Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, we're going to start this afternoon session, so welcome everybody. Welcome to the Semantic Computing theme of the Paris Software Summit. So in this theme, this is a theme where we already acknowledge that data has become a first-class citizen, and what we are interested in is how can we now start making sense of data? How can we go from data to information, knowledge, and eventually intelligence? To do so, we have several talks lined up. This afternoon, we have a couple, and tomorrow morning too, where we will be looking more at scale in the morning. This afternoon, we're going to look at some inferencing and some web science technologies and how they can bring us to this path I was talking about. So to start, I'm going to welcome Zubin Gharamani for the first talk. And let me give you some introduction. So first of all, I noticed that you have actually positions in 3 continents, which is not usual. So one of them in the US, the United States, at Carnegie Mellon, another one in South Korea, and the one where I think you reside, though, most of the time is at the University of Cambridge, just across the channel. Zubin Gharamani is currently Professor of Information Engineering at the University of Cambridge, as I just mentioned, and he drives activities for the machine learning group, and he also coordinates cognitive systems engineering. And today, he's going to talk about probabilistic modeling and knowledge representation. Zubin, thank you.
Okay, everybody can hear me fine? Thank you, Evelyn, very much for organizing this session. It's a great pleasure to be here. I'm going to talk about probabilistic modeling and knowledge representation. And my starting point is, as Evelyn hinted at, the idea that data is all around us. So we're really living in an era of abundant data. And in a sense, we're in an information revolution right now. Data is all around us in society, the web, social networks, mobile networks, etc. The sciences are becoming very data intensive. You have large-scale scientific experiments producing lots of data. The business world is relying more and more on data to produce a commercial advantage. And all of these leads us to needing tools for modeling, searching, visualizing, merging, and understanding large data sets. So this is kind of the starting point of a lot of the things that I'm interested in. And a lot of what we do is build modeling tools in our group. So our modeling tools, if we want to build them to handle these kinds of data, need to have a few desiderata. One of them is that they should be able to faithfully represent the uncertainty in our model structure and the parameters and noise in our data. There's a lot of data, but it's very noisy in a lot of ways. Our modeling tools should be automated and adaptive. They should be robust, and they should scale well to large data sets. So the approach that we tend to take in our community is a probabilistic modeling approach. And the basic idea is, if you ask yourself, what's a model? Well, a model describes data that one can observe from a system, whether it's a biological model or a physical model or a model of the web or anything like that. And so if we use the mathematics of probability theory to express all the forms of uncertainty that we have about our model and all the kinds of noise associated with our model, then we can use what used to be called about 100 years ago inverse probability, or Bayes' rule, and that allows us to make inferences about unknown quantities in our model, adapt our models, and make predictions, and learn all from the data that we observe. So it allows us to invert our model to do all these interesting things. So a lot of the work that I'm going to talk about is based on this very simple rule, which is called Bayes' rule. It's a sort of axiom of probability theory, which tells us, I've written it in words here, how to convert a model. Remember, a model is, or in this case, let's call it a hypothesis. A hypothesis defines a sort of distribution over possible data that you could observe. And you may have a whole bunch of different hypotheses before you observe the data. So you need to have some sort of what's called a prior on the different hypotheses, weighting the different hypotheses by how plausible they might be. And then you observe some data. And what happens when you observe some data is that the weights on those hypotheses change. And this rule tells us how to go from our prior weights on the hypotheses after we observe the data, multiplying the probability of the data given the hypothesis by those prior weights to obtain what's called the posterior weights on those hypotheses. So Bayes' rule is a simple rule that tells us how to do inference about hypotheses from data. And a lot of key problems in learning and prediction can be seen as forms of inference. So in particular, in the field of machine learning, we're using Bayes' rule and a lot of other mathematical techniques to design systems that learn from data, that try to reason and act based on data. So it's a very interdisciplinary field, and although the term machine learning is fairly new, it's been around, maybe since the mid-'80s, the idea of building intelligent learning systems obviously has been around a really, really long time and has lots of other names and relates to lots of other areas of science and mathematics and engineering. And one of the interesting things is that, in putting down a list of these areas, maybe the surprise element comes from statistics. So it wouldn't have been clear maybe 50 years ago when people were trying to do AI in the early days that statistics was going to play such an important role in this field of machine learning. But really, statistics is the mathematics of doing inference from data, and so that's why it's ended up being so prominent. So here's the canonical example from machine learning where you're trying to build a classifier to classify data into two classes, let's say this red class and this blue class, and let's say your classifier is this linear boundary. So the ingredients that you have in almost any machine learning system are some kind of data, in this case, data points with their associated labels, plus or minus 1. And then you have a model that tells us for a new data point the probability that it might belong to one or the other class. So this is a very simplistic model where the probabilities are 1 and 0, but you could have a more soft model in a sense. And then that model has some parameters in it, this shape of this line and where it's located. And those parameters are what you're trying to learn from data so that you can generalize to new data points. So our goal is to infer the unknown parameters of our model from data so as to be able to predict future data points, so that we can classify new data points. So almost everything in probability and statistics can be written down. This is a bit of a simplification, but essentially the two key rules that you need to do almost anything are this sum rule and the product rule. And this just tells us the calculus of what happens with probability distributions. In the case of the sum rule, if you have a probability distribution over two variables, if you sum or integrate over one of the variables, you get a probability distribution over one variable. The product rule tells us if you have a joint distribution over two variables, you can write it as a product of the distribution over the first variable called the marginal and this conditional distribution of the second variable given the first variable. So using these two simple rules, we can actually write down a general framework for doing all sorts of machine learning and learning from data and predicting, building models, etc. So we combine these two rules to get Bayes' rule. That's where Bayes' rule comes from these two simpler rules. We give names to the different ingredients, and then we can write down how to do prediction based on data. So this is how we would predict a new data point x. given a data set that we've observed and some model that we've assumed. So this is a probability distribution over possible new data points, because we haven't obviously observed those new data points yet. And we can do model comparison as well. Now, one of the key things that makes this framework interesting is that if we have a number of models and we have some data, we can use this framework to evaluate how probable those models are given the data. And a nice property that the framework has is that it automatically favors simpler models over more complex models. So it has built in this idea that there's a preference for simplicity, which is sometimes called Occam's razor. So if we're trying to compare two models, M and M prime, we can write down the probability of a model given data in this way, as this red term being the marginal likelihood that we're going to focus on, times the prior renormalized. And then this marginal likelihood, the probability of the data given the model, well, how do we write that? Let's just invoke the sum rule. The sum rule tells us to compute that we would need to average or integrate or sum over all possible parameter values that model can have. So a more complicated model involves averaging or integrating or summing over a higher dimensional parameter space. A simpler model might have fewer parameters. And so how does this equation actually capture the idea that more complicated models should be penalized? Well, there's several ways of coming to that. And I've written 3 different interpretations of the marginal likelihood that capture this idea that you prefer simplicity. The first interpretation is this expression here tells us that it defines the probability that randomly selected parameters from the prior would have generated data set D. And so a more complicated model has more flexibility. It has more possible settings of the parameters. So if you generated parameters randomly from this prior distribution, then they're very unlikely to generate a particular data set D unless that complexity was really necessary to generate the data. So that's how you only really go to more complicated hypotheses if that complexity is necessary. And a couple of other interpretations are that it's the probability of data under the model averaging over all possible parameter values, not tuning the parameters to give you the best probability. And you can also interpret it from an information theoretic point of view as the number of bits of surprise at observing some data D under the model M. So this thing is measured in bits. Okay. And the basic consequence of this is that if you observe a particular data set, then you can reject both models that are too simple and too complicated for that data set. So here's an example of that in a very simple machine learning setting where we observe some 8 data points and we're trying to fit different polynomials. Obviously, if we fit a very complicated polynomial mapping from x to y, we can fit those 8 data points exactly. But when we do this Bayesian model selection with Occam's razor, we find that this model is way too complicated and that simpler hypotheses, like, for example, that it's a linear or quadratic, are much more probable than that it's a 7th order polynomial. Okay, so I don't want to talk about that too much because I want to really talk about representations of knowledge and the role of probabilities in those representations. So let's talk about the sort of role of representing beliefs in the context of AI. So imagine you have a robot, and for this robot to behave intelligently, it should really be able to represent something about the world that it's in. Maybe the location of the power source, or whether some sensor is malfunctioning, or whether it's under threat, etc. Now, inside the brain of the robot, we need to somehow numerically represent its beliefs in different propositions. And so imagine that we assign a numerical value to the strengths of those beliefs. Now you can ask yourself, what sort of mathematics should I use to manipulate strengths of beliefs in a robot's brain? And a priori, it doesn't seem like there should be an obvious answer to that. Maybe you can do anything you want. Well, the interesting thing is that if you start to say, okay, well, I want this mathematics for representing strengths of beliefs to satisfy certain axioms of common sense reasoning, which I won't go into great depth, but they're sort of written here on this one slide. These are called the Cox axioms. Things like you want to be able to use real numbers to represent strengths of beliefs, and you want your calculation of beliefs to be consistent with some basic things about common sense. But it turns out that this idea of a belief function, the belief in a particular proposition, b of x, or for example, the belief in x given that you already know y, or the joint belief between x and y, then that belief function must satisfy the rules of probability theory, the sum and product rule and Bayes rule and all those other things that I talked about before. So these rules of probability are not just useful if we're just modeling data, but we also think that they're useful for representing beliefs in an intelligent system. So they're also a path towards building AI systems, I think. But there's another way of deriving this framework, which is through what's called the Dutch book theorem, which is something about gambling. And it's a statement about what should you do with your beliefs if you're a betting man or woman. And the basic idea is that assume that you're willing to accept bets with odds proportional to the strength of your belief. So if you believe something with strength 0.9, then you would accept a bet that would give you more than $1, say $2 if x is true, and you would lose $9 if x is false. Certainly that seems like a good bet if that's your belief. Now, if that's the case, then it turns out that unless your beliefs again satisfy the sum rule and the product rule and Bayes rule, etc., then there is a set of bets that you'd be willing to accept where you're guaranteed to lose money no matter what the outcome is. And the only way for this betting or decision-making intelligent system to guard itself against these so-called Dutch books is for the beliefs of that system to satisfy the rules of probability. So again, this points at the rules of probability as being fundamental to building intelligent decision-making systems as well. Of course, this is all nice theoretically, but we have to do this in practice in real-world systems. So how do we represent knowledge in an intelligent system? And again, there are many different ways of representing knowledge, and I'll talk about a couple of them. But I want to point in the direction of something that's been, I'd say, rather revolutionary in the field of machine learning, which is this idea that we can use graphical models to represent a certain form of knowledge about the relationships between variables in complex systems. So a graphical model is simply a graph like this. In this case, this is a directed graphical model where the nodes represent random variables and the edges in the graph represent statistical dependencies between the variables. And these models have appeared now everywhere in the field of machine learning. And you might want to ask yourself, why? Why are these graphical models useful? What do they give us? And the answer is that there's sort of three reasons why graphical models have been so successful in this field. First of all, graphs are just intuitive to look at. So they seem to be an intuitive way of representing and visualizing relationships between many variables. For example, family trees, circuit diagrams, all sorts of things are written down as graphs. Secondly, graphs allow us to abstract away the relationships between variables from the inner details of the parametric form of how those variables interact. So by writing down a graph, we are able to tell things like, is A dependent on B, given that we know the value of C, without really worrying about the details of what are the joint probability distributions over those things. So it's a nice level of abstraction. And finally, more from a computer science point of view, if you have a graphical model representing the relationships between all your variables, and then you want to build a system that does some sort of inference that figures out the probability of A given C, the probability that there's a meltdown in the nuclear power plant given that the temperature reads a particular value somewhere else, then if you want to do reasoning of that kind, you can represent it in your graphical model and compute that form of probabilistic reasoning by sending messages between the nodes in the graph. So you can create a message passing algorithm that sends messages between these nodes, and in one pass it exactly computes the beliefs of the graph, and in more complicated cases you have to iterate. So graphical models are this nice intersection between statistics, graph theory, and computer science, and they've been very influential, again, in the field of machine learning. Now, if you're trying to learn graphs from data, let's say you just observe masses of data and you don't know what the structure of the graph is, then this is actually a very hard problem, because there are super exponentially many possible graphs that you could have for any particular set of variables. And there's a lot of work that's gone into structure learning on graphs. And I'm going to tell you a little bit about some of the work that we're doing in this area. But I want to point out one interesting thing. So if you have a bunch of variables that you've measured, for example, you've measured a bunch of genes in a whole bunch of experiments and you want to know how they're related to each other, you can start by running one of the standard graphical model learning methods that are out there, and it might give you a graph. But what's actually missing from that is the fact that you've only measured a few things, and the real world is actually a very complicated place. So there might be many, many things you haven't measured. So this concept of hidden variables, things we haven't measured, will be a very important one for us to think about. So let's look at a particular kind of graph, which again has proved very popular in the machine learning world in the last few years. And let's think about how we learn the structure of these graphs. So imagine we had a graph where at the bottom of the graph we have some stuff that we've observed, some measurements that we have from some sensory system or that we obtained from some database somewhere. And we want to learn the relationships between these variables by having layers of hidden variables that tell us how these variables are related to each other. So this first layer of hidden variables will capture low-level correlations between the variables, and then you might have an extra layer that captures higher-level correlations, et cetera, as you go up the levels of this graph. Now, these kinds of graphical models are not useful for everything. Okay? They appear particularly in problems that we might characterize as pattern recognition problems, for example, where we're trying to take images and learn a deep, structured representation of the content of those images. And in fact, these models are really inspired by the sorts of things that happen in our brain. If we look at the visual system and we look multiple layers up from that, there are layers of, you could say, hidden units trying to represent what's actually out there in the visual world. But the question that we might be interested in is, given some data, can we actually learn how many layers do we need? How many hidden variables should we have? How wide should each of these layers be? How should they be connected, etc.? So the way we're doing this is we're applying the basic ideas that we talked about before. And of course, there are a lot of details I can't talk about here. But the general idea is, in a sense, very straightforward. We write down some very flexible distribution over graphs and the parameters of those graphs. And in fact, it's so flexible that we're going to allow ourselves infinitely many layers if we need them, and infinitely many hidden units if we need them. And we won't represent them on a computer more than a finite number, but we allow ourselves at least to have that flexibility. Then once we write this down, then given the data, we can infer the graph structure and the parameters of the graph. And again, if we apply this to things like images of faces, then we can end up with these interesting representations of different features of the face, like mouths and maybe nose ridge here, etc. And these are the structure of this graph is learned completely just from the faces that it's observed. None of this is pre-specified. And you can look higher up in the hierarchy and see what's actually being represented at these higher levels of the hierarchy, and it's more and more global things about these data. So I'm going to skip over representing simple relations and talk about merging knowledge bases, which is a different line of work that we're doing, but where we're really motivated by trying to find a probabilistic inference solution to the problem of merging knowledge bases or merging ontologies. So at the moment, there are many, many knowledge bases that exist out there representing all sorts of really, really interesting knowledge. And they overlap to quite an extent, and it would be absolutely wonderful to have general methods for merging these knowledge bases so that we can make use of the great amount of knowledge that we have out there in a more efficient way. So the basic motivation is there's valuable information in disparate knowledge bases in the form of entity relationships. If we can merge these, then that would provide billions of facts in a very in a single place that we could then query. And there are great efforts along these lines, like, for example, this project on linking open data. And inspired by that sort of thing, and with a collaboration between my team and Microsoft Research Cambridge involving this group of people, our goal is to develop scalable and robust probabilistic algorithms for entity and structure matching of ontologies. So I'll go through that very quickly. The test case that we're going to look at is the following. Let's merge information on movies in IMDb, an ontology that I'm sure you're all familiar with, and Yago, an ontology based on data from Wikipedia, WordNet, and GeoNames. And so if we start with this problem, we see that there are actually a lot of very interesting challenges that need to be solved along the way. So I'll just go through some of those challenges. There's a challenge in size. Yago has 400 million facts. IMDb has 23 million. There are different numbers of relations. But clearly, IMDb is about movie, and Yago is about all sorts of things. So we can limit that to the movie-related part. Obviously, we'd want to do that in an automated way. But for now, let's just do it by hand. And then we get more comparable sizes here. And then again, we can limit to common relations, which we've written here. And now the scales have reversed. Yago only has 840,000 facts. IMDb has 17 million. There are challenges in the way the data is represented. Names are represented differently, human names and movie names. There are mismatches at the concept level. There needs to be normalization by hand. But again, the real challenge would be to create absolutely automatic ways for inferring how to normalize a text across different ontologies. There are challenges in granularity. For example, in one case, you might represent a whole TV series as one entity. In the other case, you would represent perhaps every episode as a different entity. There are challenges in different information coverage. But again, that's an opportunity. We want to get greater than the sum of the two parts by combining these ontologies. And where we've gotten to so far in this project is that we've managed to get a procedure that will do exact matching of some entities. And starting from those exact matches, we can propagate the knowledge that we have in those exact matches to be able to match additional things in the two ontologies. So the exact matching procedure gives us about 20%, and we need to go the extra 80% or so to be able to really do the matching. So if we represent ontology merging as a probabilistic inference and learning problem, we see lots of probabilistic inference problems everywhere that we look here. Are these two entities the same? Are these two relations the same? Can we learn the string transformation in an unsupervised way between how things are represented in two ontologies? Given examples, can we learn a good cost function or probability model for doing the matching of ontologies? If two ontologies disagree, which one is more reliable? How do we combine the information in that way? And how do we generally represent uncertainty about facts in our ontologies? And so this is what we're doing currently. We're trying to tackle all of these problems. So to summarize, I talked about a general framework for probabilistic modeling and Bayesian inference as two sides of the same coin. Then I talked about Bayesian machine learning in the context of learning graphical model structures, which is one form of knowledge representation. And finally, I told you about some of the early work we've now been doing on merging ontologies as an inference problem. Okay. Thanks.
Thank you. Let's thank our speaker. We probably have time for one or two questions.
Hi. Hi, my name is Peter Litwin. I worked many years ago on something called multi-database systems, and Devil advocates question. We know the problems, the challenges that you enumerate for last 30 years, at least. What is kind of warranted that your approach is better than thousands of approaches that have been proposed till now?
I think that's a perfectly good question. So I'm not claiming yet that our approach is better than anything. But I'm coming in as a machine learning researcher who's interested in learning and inference, and in a sense discovering the rich world that there is in merging ontologies. And I hope that if we take a fresh approach to this, we might be able to contribute something to the, as you say, decades of literature that has been worked on in this area. So certainly, I don't want to claim until we have some evidence that anything that we do is better than anything that has been done before.
Any other question?
Hi, John DeMang from the Open University. So when people do learning on the web, one of the tricks they use is the fact that you have multiple sources. So you just do a vote, because there are 10,000 mentions of where Paris is in France. Mm-hmm. So do you think that once the web of data grows and you have multiple sources, you're not just comparing two, but 10 or 100 or even 1,000, that your problems will, some of the problems you have will just go away?
I think that certainly the more information you have from different sources, that presents both opportunities and challenges. So the opportunities are, as you say, maybe you can just vote and it'll resolve the ambiguities that you have. But there are certainly cases where simply voting is not going to get you very far because those sources are not independent. The idea of voting is only really useful if those sources of information are independent. And the challenges are also then the scale of the problem gets bigger if you're matching multiple things at the same time. So we focused on just matching two things now, but clearly matching three things simultaneously should be somehow better because you can do things like voting as well. But we'd like to think, rather than an algorithmic approach which just says, let's vote on something, we'd like to treat that as an inference problem where perhaps if you know one of the sources is unreliable from other votes disagreeing, then you would downweight one of the sources versus other source. And you can do all of that in fairly ad hoc ways, but you can also do that by thinking about hidden variables representing the reliability of different sources. There's a lot of very interesting research, some of which actually from Microsoft research at Cambridge, on how to combine different unreliable sources of information.
Thank you. Let's thank our speaker again. And I'm actually personally very interested in learning what you're going to learn in the future and how this can apply to, when you start talking about petabytes, exabytes.
Yep.
Thank you. Our next speaker is Stefan Stab. So from the University of Koblenz. So one characteristic about you I found is that so you are both an academic, but you also have 1 foot or maybe 2 feet in the entrepreneur world with enterprise. And otherwise, so Stefan Stab is professor for databases and information systems. His interests lie in web science and technologies for web science, in particular semantic web, web retrieval, social web and multimedia web, software web, and interactive web. Well, a lot about web, so I'm assuming large scale here. Thank you.
Thanks a lot, Evelyn. Guess you with you. Oh, it was just F5.
Yeah.
So here we go. First, maybe before I start, a few notes. What I talk about here is some stuff we have done over the last 5 years. And over the last 3 years, this has been joint work together with a lot of students and colleagues in the MOST project. Some people I should name here, like Uwe Assmann from Technical University Dresden and Jeff Pan from University Aberdeen and their teams. And this was really core to getting this going here. Maybe what I want to do first is to show you the kind of overall vision that we want to produce here by including ontologies and ontology technologies into normal software modeling and development lifecycle. And if you take a very long-range perspective, what you see with software languages is that we started with untyped languages, we added types, we added constraint languages describing what kind of parameters are given in a design by contract, for example. With ontologies and an ontology-driven process, you inherit a lot of technologies, especially reasoning technologies, that can give you even more power. And where does this power come from? Well, there are different extremes. You have constraint languages like OCL, for example, and they are like data log. You can do quite some interesting reasoning with them. But if you really want to know more information about the classes and their objects together, about the 2 different levels that you have in your models, or about 3 levels that you have in your models, then these kind of constraint languages don't give you the right power. So in a way, these languages are not powerful enough. On the other hand, of course, you have software verification and you use model logics, first order logics, this kind of thing there. And this is very powerful stuff, but they don't work at that level of efficiency that you quite often need for normal software development projects. And in between, over the last 15 years, we have seen a development of ontology reasoning technologies that let you work with large models in a pragmatically feasible way and do reasoning and do help the software engineer. And so what we see from these new technologies that have been developed over the last 10, 15 years is that you can do all kinds of consistency checking with your software models that we think are quite interesting. And you can not only do some checking, but you can also give some advice as to how to improve the models or where the problems are with these languages or these models. Now, how did this start off? It started off with a rather mundane thing. We have these 2 pillars here. This is the ontology world, where I come from, working on the semantic web and different types of applications there. And of course, there's the software modeling pillar. And of course, when we had these ontologies, we also always had software code to actually build applications. And in these applications, ontologies were used. And that's, of course, core to the ontology world, that somehow these ontologies are models that are visible to the user and interact with the software. So here, I have to thank Subin because he already brought up some of the ontologies that are in use. Here are some other ones, especially in the medical domain. They're really big ontologies that are used in actual systems. So SNOMED, or the foundational model of anatomy, they have a few hundred thousands of entities in these ontologies. That means concepts and relationships that are there and that are used by actual systems. And, well, if you go to the business-to-business world, you have terminologies. Some project partners of mine, they counted that there are like some 500 terminologies. They are not necessarily yet in the OWL or RDF format, but they should rather be in order to improve their management. Now, at this point, when we developed applications that would use these ontologies, I was quite frustrated. Why? Because you had the ontologies on the one side, and you had the software development on the other side. And the bridge between these two worlds was rather loose. And it was very inconvenient. And once you would start developing your models on the one or the other side, you would lose the connection between the two sides. And the software would break very easily. So I was always frustrated by having my applications break all the time. Because the ontologies are continually evolving, and of course you need this new piece of software component that you include on the left-hand side. So then 2006, there was a PhD student coming in and said, well, we have this problem. How can we deal with that? And he had the very good idea to say, well, we need to look at how the ontology technologies fit into our software development models. So in the rest of this talk, I don't talk about how nice or big or something SNOMED or FMA are. I talk about how do these ontology technologies actually fit into our software models. And I want to show you two examples of them without saying that these two examples cover everything. So especially in the MOS project, we had a kind of staged approach then to say, well, of course, first we need to look at the basic technologies that are around on these sites. So there are model-driven software development, and you have a lot of different tools. You have different modeling languages, you have transformational languages, and you probably know them better than me, because I think many of you are software engineers by heart, where I come rather from the ontology side. And then in the ontology side, you have reasoning technologies, description logics reasoning, which is a subset of first-order logics, and give you sound and complete reasoning for pragmatically large ontologies. Worst case is always like too bad to do anything, but pragmatically you can come up with rather big models and still reason with them in a decent time. And of course also in this project we were developing some tricks of the trade, and Jeff Pan especially wrote some very nice papers about to do approximations and to get a lot of feedback, correct feedback in very short time, improving available performance even more. On top of these basic technologies that we use in order to support ontology-driven software development, we then looked how can we bridge between these two different worlds. And I want to look a little bit into how does such a bridge look like, how can we do some consistency checking, and how can we then support the software development lifecycle and provide some guidance with that. I want to show you two small case studies depending on time. Maybe it's just one. Let's see. So the first one is about including ontology languages into domain-specific languages. And why that? Well, the generic picture we have there, we had there in our case study, was we have a user of this domain-specific language. And I will show you what this domain-specific language was and is. And, well, in the usual sense of domain-specific languages, of course, the user would develop a domain model. And the domain model, of course, would have to correspond to some meta model which prescribes the abstract syntax. And in the case of our case study, we had a software company, Comarch, from Krakow, Poland, and they had software developers who would prescribe these domain-specific languages. These domain-specific languages, of course, again, need to adhere to some meta modeling languages in order to prescribe the language below. So you have the typical meta modeling approach that you would also have with MOF, for example. And in our case, we looked at how can this meta modeling language that you use in order to define your domain-specific language look like, and how can it help at this level of developing this domain-specific language as well as at the level below where the DSL user is acting, in order to give some guidance to the user and in order to ensure that we have sufficient constraints at the language level. Now, why is this interesting? Why is this different from, let's say, having some OCL constraints in your different models? It's interesting because the idea is that with ontology reasoning technologies, you specify these constraints once, but then you can employ them at 2 and with more recent models even at 2 or 3 layers and reason over these different layers at the same time without having to specify the constraints anew, while in typical OCL constraints you would rather have for each layer an independent set of constraints where you would not quite know whether they fit together very easily. So what is the case study? The case study was, as I said, at Comarch, Poland. Now they are very successful in developing and selling network software infrastructure. So they're telecommunication providers buy their software, and with the software they can then administrate different types of routers. You name the different companies, and they support for the telecommunication providers these different configurations. Now, when you look at the domain model, what they need is for the different types of routers that are supported, you have these different devices. There's a lot of flexibility in setting up this device with having different slots, different operating system modules, and different engines that run for these individual devices. And I must confess, I'm not very good at this domain, so you can ask me a lot of terrible questions that I cannot answer. Typical restrictions that we would have there are, for example, a Cisco device having some configurations coming with some engines, and you need some stuff in order to run this device successfully. These can become quite complicated rules. And what you need there is you need, in the end, a designer of the language that allows, that gives to the user a language where the user is easily capable of providing the right stubs into the right slots without thinking a lot about whether it's a formal or informal language. The user should just be able to push in some slots and get the correct feedback without bothering a lot about what is the exact language. But the DSL designer, of course, he should do a bit more work. And the status quo at Comarch was that basically they had a very simple domain-specific language based on XML. And the funny stuff, of course, was that with just having XML, you could produce all kinds of invalid configurations, and you would have to develop some Java code, which was not really declarative, that would then have to check whether what you do there really makes sense. So you could say there was not a lot of declarative mechanisms built into this domain-specific language mechanism. Here you see a few more of the things that a user should have from such models. So the user should be able to configure something and say, well, I need such a hot-swappable OSM. But then, of course, this may be problematic. There may be an inconsistency. And, of course, that should be signaled. The interesting thing here is such a signaling should come early. The good thing about ontology reasoning technologies here is that you can reason about partial knowledge. So when you recognize that there is a configuration that's not completed yet, but that's already inconsistent, you can discover this. But you don't have to prescribe exactly what are all the possible combinations that could eventually become inconsistent. You really just have your domain model, and if there's an inconsistency showing up early, the reasoner finds that. So that's nice, because then you can signal the user, here's a problem. And maybe just another side note here, it's of course also an interesting capability, because it's a capability where users of this web ontology language often get confused about. It's called the open world model. And people don't like that very much. They don't understand what open world is versus a closed world, as the logicians call it. But if you call it to these technicians and say, well, that's a model that you're currently drafting, versus that's a model that you then will deploy, they understand that a model that you draft behaves differently and has different consistency requirements than a model that you deploy. And the reasoning naturally supports this distinction between drafting and deploying a model. So what are these requirements that the user has? Well, checking, debugging such models. Then, of course, what you needed here in order to become consistent, you need first some slots into this configuration. Then you can insert a hot swappable OSM. And you can even suggest to the user what's now possible to insert here so he doesn't have to look around a lot. And then, of course, you can add things. And again, there may be inconsistencies, maybe here, because you don't have a specific card inserted. And the reasoning can suggest to you that there is a specific configuration that does not follow the model that you required in the background. So in this sense here, you come up with explanations, and hopefully at the end the user comes up with a consistent configuration where you can even specify in more detail what the user has exactly configured without giving all the details, namely such a Cisco 7603 device. Now you could say, well, isn't that the kind of expert systems we had 30 years ago? In a way, you could say, well, to some extent, yes, because it's offering the kind of capabilities. To quite some other extent, no, because now I want to show you a bit how this is developed by Comarch now, using the framework and not looking at exactly what is the exact procedural knowledge that I need to build in, but rather how should the software models look like in order that I get this kind of behavior. And that's, of course, quite a different twist to producing the same kind of capabilities with less work. Okay, now I want to show you a little bit code. I'm not sure whether that's appropriate here for this kind of talk, but I thought I'd rather show something very concrete so you know what's going on. So here you have the domain-specific language. That's what Comarch is using now. And, well, it's not very unusual. It explains some of these devices and how they fit together. Now, the idea was that we extend the domain-specific language that they almost use, structurally at least, with some of the capabilities that description logics reasoning, ontology reasoning technologies offer. So that's the piece in red that you see here. What you do here is you describe what are the features that should be fulfilled such that an object belongs to a certain class. That's basically it. So it's not very different than the normal conceptual modeling you do, let's say in a UML class diagram. The only difference being that the capabilities you have here are more powerful from the reasoning side. So you could even go and say, I take a UML class diagram and push this into the reasoning engine, and already there you may get warnings, inconsistencies, and so on, and people do this and can work on that. Of course, if you make the language a little bit more powerful, you can express more constraints on your domain-specific language. So the domain-specific language that's crafted here has these ontological restrictions. Now here, you see this on the upper right corner. That's the job of the DSL designer. That means it's not a matter to the user to understand what these restrictions on the classes really mean. The user in the end should only just know there are some nice buttons that he can push and he gets an explanation of when things go wrong and not more. Now, description logics, which corresponds to these red parts, as a subset of first-order logics, gives you reasoning at two levels. So you can reason now about this language that is crafted here, whether it is consistent in itself, or whether you defined a language, or whether you define a piece in the language that you cannot instantiate without violating the models. So you get some notion of consistency of your domain-specific language directly for the DSL designer that's depicted here in the upper right corner. And then you get reasoning at this object level for the user who uses this language in order to fill in specific slots. It's sound and complete reasoning. If you want to speed up, you can of course say, okay, I'm only interested in some approximation, and quite often this is also useful. It's pragmatically efficient. Some of these ontologies with several hundreds of thousands of concepts, they need a very long time to reason about, but that's not quite surprising given that they have several hundreds of thousands of entities. If you have several dozens or several hundreds entities, then you typically end up with very well-behaved effects from this reasoning process. Now, what have you seen? You have seen the user side of it, user side getting feedback. You have seen the person at the software development company, specifying a domain-specific language. Also, he is getting feedback about whether this language is consistent in itself. And as well, the user is getting feedback. But how can you do that? How can you specify this language? Well, for this purpose, for this case, we have developed an integrated meta-meta model. So to bridge between the two pillars of the Ontoware on the one side and the software development bots on the other side, there's now this integrated meta-meta model that allows you to instantiate entities which belong to the ontology space as well as to your normal, for example, UML modeling space. So with using these modeling constructs, you can at the same time do your kind of normal modeling process as well as benefit from the reasoning process to the extent that the reasoner supports this. And what you see here is on the left side is the reasoning process with the two levels, T-box and A-box they are called. You can query there the ontological structures and reason about them. And on the right side, you have all the tools that you would typically use in model-driven software engineering. Now, the nice thing about this, and that was also a nice part of this cooperation in the project, that then the project partners at Comarch, they also looked into whether this would be of any help to the people that would use this framework. So they looked at productivity, they looked at quality, and they looked especially in the first place now at the DSL designers. How difficult is it for these designers to develop such a domain-specific language and then get some feedback? And of course, the assumption was that you want to have a language without errors, without mistakes. So, of course, you have to also measure the bugs that you produce there. So, the nice figures for us that they came up with was they looked at how did people do it before, because they had this already as part of their process, and what happens once you include the ontology reasoning technology into this game. And what you see here is a productivity improvement of 30% and a quality improvement of almost 50%. And maybe offline I can give you more details about this worked out exactly. I run a little bit short of time to go also into process reasoning with ontology technologies. Here the idea was basically, and that was a case study with SAP. SAP has several stages of development, and here I try to set this apart between Dilbert and his manager. The manager says, well, we need a process that says, select applicant and hire him. And then the developer comes up and says, well, it's not exactly how the process works. But of course, the question in the end of the day is whether what is developed still corresponds to this high-level specification. And at SAP, they have 3 to 4 layers of specifying how this process works exactly. Now, at the end of the day, you may ask, is what you have on the right side still the thing that you wanted to have from your business point of view on the left side? And we do some ontology reasoning for this in order to answer this question. And here, I jump a little bit. Here what you need is a different kind of bridge. You don't need a bridge where you have a joint meta model between those two different areas. What you need is a transformation bridge where you compile these, here it's BPMN processes, into ontology reasoning technologies, and then do the reasoning and deliver the corresponding results. And here I do a little bit fast forward in that because I jump directly again to the evaluation that colleagues at SAP did. They looked at some of the normal cases they have from their development life cycle, and then looked at how difficult it was for people to find the problems and to repair these problems, and gave this challenge to different people within SAP, people within our project, and also looked at how these would behave differently. Actually, it was similarly difficult or simple, you could say, for each of these different groups of people to come up with the correct answers. But if you compare the different technologies without the support or with the support indicated here with this red arrow, then they came up with some numbers about savings of productivity or quality improvements. And again, we are in a range that makes it really worth it to look at this process using these reasoning technologies. So what I tried to indicate here was that by including these ontology reasoning technologies, and by building bridges between these two areas, and I've shown you here 2 bridges. One bridge was an integration bridge where we would have a joint meta model that would allow you to go into two different pillars in order to do what you wanted to do there independently. And the other one was a transformation bridge. And there you would compile some model aspect into the reasoning representation in order to come up with the problems that you find there. And you can do this at different layers and use this as different layers. At the M3 layer, following the normal OMG nomenclature, or at the M2 layer, each time you can look at what does it help me to do this transformation or this integration. And you have seen some of these cases, like the configuration case. There are other cases which we have looked at in this project. And for example, here, the owlizer case would transfer a normal UML model into ontology reasoning in order to check the problems that come up in this normal model. So what is a takeaway message for you? Well, we had a couple of original contributions here, which was about these two builder pillars, which came in the beginning from quite a different end, namely from the end of this frustration of having to somehow link these two different worlds. By linking these two different worlds, what we saw was that it's not just convenient for ontology applications, it is too, but it's also convenient for normal type of applications where no real ontologies in the original sense are really participating. And we have looked at here at domain-specific languages and process languages. The marriage is not quite trivial, and we still learn how to do it. And we look at other cases. We'll look at cases where reasoning is not only spanning 2 levels, but 3 levels of reasoning. There are terminological problems. I told you about this problem of calling an open world, a closed world, as the logicians do. And that always gives trouble to the software engineers and database people because, well, the database persons typically talk about closed worlds. But once you find the right terminology, like this is a model that's currently drafted, and this is a model that's really finalized and should be finished, and no further mistake or problem should be in there, then people start also to understand what this technology is doing for them. And finding these translations is important. You can see some productivity gains. And if I have to look forward, what I see and what I try to generalize here is that these are the ontologies in the original sense. They contribute some knowledge by the domain experts because these ontologies are typically not built by software engineers. The FMA has been built by doctors. The gene ontology is built by people in this bioinformatics domain. So they contribute knowledge about their domain. Not using that, I think, is a lost opportunity. When you include it, there are so many ways you can do it, and we're still figuring it out. We're playing around, for example, with families of business processes. We're reporting a paper on that. We're playing around with software product lines where this domain knowledge is important, and that seems quite useful to have there. We think that these terminologies should be reused, and when we look at different software components, different software projects, what we also see is then it's not just that we have this knowledge confined within one project, but typically you have many projects that run next to each other and in the end should play together. And quite often they don't. But capturing knowledge about how they could or should play together is one of the tasks we want to tackle. And we think that semantic technologies, ontologies, and semantic web formats like RDF are the right answers to respond to these needs. And here are some references of our own work, also to some work by other people. And thank you for your attention.
Thank you. So we have time, yeah? Sorry, in the back.
Okay, yeah, thank you for your talk. I'm Gregor Engels, University of Paderborn. I can understand that you can help us as a software engineer on the structural side, but the bigger problem in our domain of software engineering is how to deal with behavior. It means how to deal with dynamic things, and I can understand that you can help me that I build the right object diagram, but this is not so difficult for me or for my software engineers.
You can
so my question is there also any, can you say something about the future, how you also can help on the dynamic side?
So, I mean...
I have a second question before I lose my micro. The second one is that in the second example, you spoke about these transformations. I missed the word semantics because you are changing the language from one side to the other side. And what is about semantics?
Mm-hmm. Okay, very good questions. First about, the first question was about the question about can we do more than structural diagrams, more than, let's say, human class diagrams? Yes, we can, but to some extent we can only do structural analysis on other models. So, for example, we looked at BPMN and we did structural analysis on these models. And this gave us already quite some feedback about what was problematic in these models. And people at SAP also compared this to PatriNet analysis, for example, with some ups and downs for both these two technologies. Can we do really reasoning with state changes? No, that's outside the realm of description logics reasoning. Well, maybe people come up with other kinds of neat integration of, let's say, some model logic with parts of description logics in the future. I don't know. Would be a good research question, probably. Would still, maybe to some extent, this could still be even pragmatically efficient or cover something. I don't know. It's really speculating. But right now, I would say no. You cannot describe state changes. What you can do, you can describe structural aspects of dynamic behavior. When you look at then the other question about what happens with these transformations, one interesting question I think is that you have these processes that we can also describe structurally in description logics. What I would like to include there with these processes are also the terminologies. We didn't do this until now, but actually that's one thing that I would like to do, to say I have different process steps, and for example, if we merge two companies, then, well, the one company had one way of calling their process steps and the other company had another way of calling them. And you could at the same time look at these processes structurally and look at their terminology. And then look at what does this give us if we combine these descriptions of behavioral aspects. It's not everything, but I think that would be quite interesting research activity to perform. I think that was it.
Okay, my question is somehow related to the previous question, and it is also related to my previous work on multilingual generation, multilingual natural language generation, so that the idea was that you have a formal specification of software, and from this formal specification, if you have the right grammar, you can generate the user manual for this software in so many languages, right? And the problem in this case is that any formal specification of software, it misses one part which is most crucial for the user manual, and this is a plan for operations. So in order to do this, you need to implement a sequence of steps, right? And just my question is about the way of, on the one hand, of getting this out of the formal specification. And what do you think about the possibility of representing this in terms of your A boxes? I think that something to this extent was in your presentation you skipped in your experience with SAP, but I'm not sure.
I'm not sure I understand the question. I mean, what you seem to suggest to me is that you have some approach like either literate programming, or you have these models and you try to automatically generate the natural language that would come close to some literate programming from these descriptions. I must say the idea is around, for example, in the ontology area, to describe ontologies with natural language. I have not seen a convincing solution for this problem until now. It would be good to have such a convincing solution because people have problems looking at these ontologies, these formal structures, and understanding what they mean. So it's still an unsolved problem. And I think the problem is even more difficult if you consider software modeling in general.
Well, let's thank our speaker again. And I would love to continue the conversation, but we need to break for the afternoon break. If you are still interested in learning more about making sense of data, there is another session tomorrow morning. Thank you.